This video involves 3 different chemical reactions which are critical to the history of the world. You need to identify them, essentially. I don't think you really need to memorize them, except for one of them I think you should just know, and it's not that hard. Okay, one of the reactions is called saponification. Saponification is called soap. It's basically soap making. The other reaction is fermentation, which leads to the production of alcohol. And that's not because alcohol, like drinking, is necessary for civilization. The formation of alcohol allows you to store things. All right, it's not just about alcohol. It's about fermentation that produces yogurt or cheese, or produces kimchi, if you like kimchi. And if you don't know what kimchi is, you should try it. It's really good. It's fermented cabbage. It's Korean and it's tasty. And the final reaction is combustion. If you can't burn things, you cannot make fire. And if you cannot make fire, you cannot cook your food. And food tastes much better when it's cooked. That's just my opinion. Of course, sushi is good too, and it's not cooked. But the rice is cooked. So there you have it. Anyway, saponification, soap making. So what people discovered at some point in history was that they smelled. Yeah, and that there were certain chemicals you could produce that would remove the smelly stuff from your body. Now, when you smell, it's because a lot of smelly compounds are trapped into the oil in your skin. So if you can find a way to remove the oil from your skin, you can remove the smelly molecules with the oil, and that's what soap essentially does. Well, what is soap? Well, soap was originally produced by this. They discovered that couple things. First of all, if you were to burn a piece of wood in a fire or something like that and let it go, and you could pick up the ashes at the end, the ashes actually usually contain alkali. Okay, and that just means of ashes, but alkali also means a base. Now, that ash would contain some sodium hydroxide and some potassium hydroxide, or actually it would contain sodium oxide and potassium oxide, but when you add water, it turns into sodium hydroxide and potassium hydroxide. If you mix that in a container with some lipids or fats from animals or even from plants, you end up making soap. And this is why. This is what happens. A lipid is a really large molecule. It has 3 carbons in a row here, linked by an oxygen, by 3 oxygens, to 3 long chains right here. Now these chains, I couldn't draw them out. They're like 20 or 30 carbons long. I didn't even put all the hydrogens on them. But these long chains can undergo what's called hydrolysis. And what that means is we're going to break this molecule into parts, all right, in the presence of the base. And so what you end up getting is you end up getting this thing right here, which is called glycerol, but it's an alcohol. If you look at it carefully, you can see the 3 OHs, okay? Glycerol is also known as 1,2,3 propan triol, because it's got 3 hydroxides, 1,2,3, and that's an alcohol. But that's not, and that can be used to make those. That can be used in a further process to make that clear soap stuff. You know, the soap that you buy that's transparent, but not the regular soap that you buy in the bar. All right. What's really important is you get this right here, the long chain of carbons, and at the end, the sodium goes with this part right here. It sticks to it. Now, what's interesting in this particular case is you get a molecule that's what they call amphiprotic or amphoteric. What this basically means, amphi means 2 things, like an amphibian. Now, there's a lot of history here, a lot of explaining, but it's kind of worthwhile. And again, you don't really need to know much. You need to recognize this big molecule here, the base, and it makes basically soap. That's why it's saponification. This, to me, is an interesting topic. So, in the olden days, the Romans did not have soap. The Romans didn't like soap. They thought that was for people from the Middle East, and, they didn't think that was civilized. What they would do is slather themselves with olive oil, and then they would have their servants scrape the olive oil off them, and then they would scent themselves, and so they wouldn't smell so bad. Okay? People in the Middle East, they were making this stuff called soap. They would take a fat, react it with a base, and they would get the stuff glycerol, but the other product that they would produce was this thing. And this is an interesting molecule, because here's the thing. This is all carbon and hydrogens over here. It's basically symmetric, and it's basically nonpolar over here. This part, the other part of the molecule, has charges. This is not just polar. This actually has charges on it. Now, the way this would work was this. You go into your shower and you scrub this stuff all over your body, okay? This stuff, this part of the molecule is nonpolar and likes oil. So it sticks, remember like dissolves like, so this sticks to the oil on your skin. This stuff is polar and charged and it likes the water. So essentially what soap allows to happen is basically this part of the molecule sticks to all the oils and the smelly molecules that are on your skin, right? And this part here sticks to the water. And so as you're taking your shower and you start scrubbing, the oils on your body start to stick to this part, but then the water sticks to this part, and then the whole molecule, along with all the oils from your body and the stinky stuff, goes down the drain. Okay? And that's because the molecule is one part that likes oil and one part that likes water. In fact, what this allows to happen is allows oil and water to mix. And when you're making the foamy, that's what's actually happening when you're making the foam. Okay? You essentially are making a emulsification is what they call it. And you're allowing the oil and the water to actually mix together. Now, that's saponification. How much do you need to know about that? Not much, just recognize it. All right, fermentation, really, really important. Now, you might think fermentation is about making beer or, alcoholic beverages, but the reality is fermentation is super important, okay? This is my attempt to draw a slice of bread, okay? Over this quarantine or whatever we're having here, I have literally learned I baked bread like 8 times. I can make sourdough bread now. That's something that I managed to learn. What is fermentation? Well, you have organisms. Yeast are an organism. They're a microorganism. They are a eukaryote, which means they have a nucleus, and they can take sugar, okay, and because they have certain enzymes, they can turn sugar into 2 things. Alcohol, now this has got 2 carbons, so this is ethanol, and carbon dioxide. Now the bubbles are what makes my bread rise. So when I'm making bread and I let it rise, what I'm allowing to happen is fermentation. There's a small amount of alcohol being made, but the gas bubbles do get trapped in the slice of bread, okay? And what happens when you bake the bread, the gases expand because temperature's going up, and the bubbles get bigger and the bread rises. This reaction is so important. And it's not because people like drinking. Obviously, yes, you make alcoholic beverages with this, but it allows you to bake bread. Think about it. No pizza. No pizza. Okay? No hamburger buns. No bread. Also, fermentation involves the production of cheeses, yogurts, okay? And again, I mentioned kimchi, which is really good, and you should try it. All because of the process of fermentation. All right? By the way, you make 2 molecules of the alcohol and 2 molecules of carbon dioxide, which gives you a total of 6 carbons, which is what you had in the original sugar or glucose. You should know this reaction. You should know that fermentation involves sugar and that you're making alcohol, specifically ethanol with 2 carbons and 2 carbon dioxides, and those are the bubbles in the bread or the bubbles in the beer or the bubbles in the champagne. If there's no bubbles in the alcoholic beverages, that's because they allowed the bubbles to escape. As a matter of fact, when you make wine or beer, you have to allow them to escape to some degree or your container might explode. Not a good thing. Next. Combustion, which we've already covered. A combustion reaction is something in which there is a hydrocarbon reacting with oxygen. Now, the products are always assumed to be CO2 and water. I'm not going to bother balancing these guys again, okay? Now, this is propane, this is barbecue gas, and this is methane, this is stove gas, right? And you react with oxygen, make CO2 and water. The assumption in all these reactions, by the way, is you have excess oxygen. Okay, it's a really important assumption because if you don't have excess oxygen, what you'll end up making is you'll make carbon compounds with less oxygen. So you might make carbon monoxide, right? This is carbon monoxide. I always forget whether it's monooxide or just a no. Okay, you make carbon monoxide, and carbon monoxide can be deadly. If you really take away the oxygen, what you end up making is pure carbon. And that's how you make charcoal. Charcoal is made from burning wood in the absence in which there's a very, very limited amount of oxygen getting to the wood as it burns. And it burns a lot slower, and what ends up happening is you end up having pure carbon when you're done, and you can squish it together and make briquettes, and this way you can have a barbecue. So, a barbecue that doesn't involve, propane. So if you actually use charcoal briquettes on your barbecue, somebody had to burn some wood first to make the actual charcoal. However, it's said to be not completely oxidized because there was not enough oxygen around, and then as you burn the charcoal, the carbon that gets further oxidized to produce CO2 and water again, just like it would have if there was oxygen around originally. That's combustion. Also very important. One likes to cook things, one must do combustion, I assume. Unless you have an electric stove, but I kind of like fire better. Anyway, have a great day.